Imagine for a moment you're an astronomer scanning the night sky, and suddenly your instruments detect something extraordinary, a burst of radio waves so powerful it outshines entire galaxies, lasting barely a millisecond before vanishing without a trace. This isn't science fiction. This is the reality astronomers have faced since 2007, when they first discovered what we now call fast radio bursts. These enigmatic signals from the deepest corners of space have become one of the most compelling mysteries in modern astronomy, cosmic messages that arrive without return addresses, teasing us with their brief but brilliant appearances. Each burst carries more energy than our Sun emits in 80 years, yet we still don't know what creates them, whether they're the death cries of collapsing stars, messages from advanced civilizations, or something even more extraordinary that we haven't yet imagined. What makes fast radio bursts so fascinating isn't just their immense power or mysterious origins, but what they represent in our quest to understand the universe. These signals travel billions of light years across cosmic voids, passing through galaxies and magnetic fields, collecting stories about the fabric of space itself along their journey. They're like cosmic telegrams that have crossed the universe, and we're only just learning how to read them. Every new detection brings us closer to answering fundamental questions about the nature of reality, the structure of the cosmos, and whether we're truly alone in this vast expanse. The pursuit of understanding these bursts represents humanity at its most curious and determined, always reaching for answers, always wondering what lies beyond the next horizon. Join me as we explore 25 crucial clues that scientists worldwide are using to decode these cosmic puzzles. We'll journey from the deepest space observatories to the most advanced supercomputers, from theoretical physics to cutting-edge technology, uncovering how each piece of evidence brings us closer to solving this magnificent mystery. Together, we'll examine the patterns within the chaos, the repetitions among the random, and the subtle signatures that might reveal whether we're witnessing natural cosmic phenomena or something that could fundamentally change our understanding of existence itself. This isn't just about astronomy, it's about the human spirit's relentless drive to explore, understand, and connect with the universe in ways we're only beginning to imagine. Our story begins not in the depths of space, but in a university archive where astronomer Duncan Lorimer and his student David Narkevic were sifting through old observational data. The year was 2007, and they were analyzing recordings from the Parkes Radio Telescope in Australia, originally intended to study pulsars. Buried within that mountain of data, they found something that should not have been there, a single colossal spike of radio energy that leaped off the charts. It was a 5-millisecond burst so powerful and so isolated that it defied all immediate explanation. This wasn't just a new discovery, it was the birth of an entirely new cosmic mystery. Because it was found in archived data, this first burst became known as the Lorimer burst, a celestial event that had already occurred years before anyone even knew to look for it, reminding us that the universe is full of secrets waiting to be uncovered. The sheer intensity of this signal is what makes it so difficult to comprehend. To put it in perspective, that first fast radio burst released more energy in that fleeting 5,000th of a second than our Sun emits over 80 years. Think about that for a moment. Our Sun, a raging nuclear furnace that has sustained life on Earth for billions of years, is utterly dwarfed by a cosmic event that is over in the blink of an eye. This incredible energy, compressed into such an infinitesimally short time span, creates a paradox for astronomers. How can something so brief produce something so powerful? It implies a source of almost unimaginable violence and efficiency, a cosmic engine capable of focusing stupendous amounts of energy into a tightly beamed flash that rips across the universe. Detecting these millisecond mysteries is like trying to photograph a single frame of a movie playing on a screen a million miles away. Our radio telescopes must constantly stare at vast patches of sky, hoping that in the exact fraction of a second they are looking, a flash will occur. It is an endeavor built on immense patience and a little bit of luck. The very brevity that defines them also protects their secrets, giving scientists almost no time to react or to study the event across multiple wavelengths of light. By the time other telescopes around the world can swing into action to look for afterglows or counterparts in optical, gamma, or X-ray light, the burst is long gone, leaving behind only a ghost in the data, a single, tantalizing clue in a cosmic detective story that spans the entire universe. This remarkable dispersion effect becomes our cosmic measuring tape. When a fast radio burst travels across interstellar and intergalactic space, it doesn't move through a perfect vacuum. It encounters a sparse soup of free electrons-charged particles scattered between stars and galaxies. The fascinating thing is that these electrons act like a subtle cosmic prism. They slow down the lower frequency radio waves just a tiny bit more than the higher frequencies. This means that if you were to listen to a fast radio burst, you wouldn't hear a crisp, simultaneous pop across all radio stations. Instead, you'd hear a descending chirp with the highest pitches arriving first and the deepest bass notes trailing behind by a fraction of a second. This delay isn't a flaw in the signal, it's its travelogue, a detailed diary of its epic journey. By meticulously measuring this delay, calculating the precise difference in arrival time between the highest and lowest frequencies, astronomers can calculate what's known as the dispersion measure. This single number is incredibly powerful. It effectively counts the total number of electrons the signal has encountered along its path to Earth. Think of it like this. If you were driving through a light fog, you could estimate the total distance you traveled by measuring how much your headlights dimmed. The thicker the fog or the longer the drive, the more the light would be scattered. In exactly the same way, the greater the dispersion measure, the more material the radio burst has punched through, indicating a longer journey from a more distant source. The implications of this are staggering. For the earliest detected bursts, their dispersion measures were so enormous that they simply could not originate from within our own Milky Way galaxy. The amount of material within our galaxy isn't nearly sufficient to cause such a pronounced delay. This was the first definitive proof that fast radio bursts are not local phenomena, they are intergalactic travelers. By comparing the measured dispersion to models of the expected amount of material in our galaxy and in the vast cosmic web between galaxies, astronomers can triangulate their source, placing them billions of light years away in distant galaxies. This transforms each burst from a mere mystery into a precision tool for mapping the otherwise invisible matter that constitutes the large-scale structure of our universe. Then came a discovery that shattered the entire playing field and rewrote the rulebook. For years, the prevailing theory was that fast radio bursts had to be one-time cataclysmic events, cosmic bombs that went off once and could never explode again. This made intuitive sense. How could something releasing the energy of 80 suns in a millisecond possibly survive to do it again? But in 2012, everything changed. Astronomers using the massive Arecibo dish in Puerto Rico detected something that defied all expectations. It was a burst from a region in the constellation Auriga, and it was given the decidedly unglamorous name FRB 121102. Then it happened again and again. This wasn't a single explosion, it was a source that was actively, repeatedly firing out these immense signals. The identification of this repeater sent shockwaves through the astronomy community. It was a revolution in our understanding. Suddenly, the door was flung wide open to entirely new categories of explanations. If the source could survive its own outburst, then it couldn't be a final, destructive act like a neutron star collision or a black hole birth. Instead, it had to be something persistent, an engine that could recharge and fire over and over again. This pointed toward extreme objects like magnetars, incredibly dense, spinning neutron stars with the most powerful magnetic fields in the universe, or perhaps some other, even more exotic phenomenon we haven't yet conceived. This repetition was the key that unlocked systematic study. Before this, trying to understand a fast radio burst was like trying to solve a murder where the crime scene vanished instantly and the weapon disappeared without a trace. With a repeater, astronomers could do something they had only dreamed of. They could point the world's most powerful telescopes at that single spot in the sky and wait. They didn't have to hope for a random, fleeting event. They could prepare. This patient vigilance paid off spectacularly. Over time, FRB 121102 didn't just repeat, it went into active, hyperactive states, sometimes firing off multiple bursts in a single hour. This provided a wealth of data, a library of bursts from a single source that could be compared, contrasted, and analyzed for patterns. With this treasure trove of information, scientists could finally begin to paint a detailed portrait of the source's environment. By studying the subtle differences between each burst from this same cosmic engine, they could infer details about its immediate surroundings. They discovered that the waves were heavily scrambled, an effect known as Faraday rotation, which indicated they were passing through an incredibly powerful and complex magnetic field. This was the fingerprint of a truly extreme environment, likely near a massive black hole or within a turbulent nebula of material. The repeater didn't just tell us that some bursts repeat, it gave us our first real glimpse into the chaotic nursery where these cosmic titans are born. The hunt for these cosmic ephemera then entered a new era, defined not just by detection but by precision. For years, astronomers could point to a patch of sky and say a burst came from somewhere in that vast area, but it was like being told a phone call came from somewhere on the continent of North America. The real breakthrough came with the advent of revolutionary radio telescope arrays, networks of dishes that work in concert to achieve a resolution far beyond any single instrument. Facilities like the Australian Square Kilometre Array Pathfinder or ASKAP and Canada's CHIME, the Canadian Hydrogen Intensity Mapping Experiment, fundamentally changed the game. Their design is the key to this new precision. ASKAP, for instance, uses a technique called interferometry, where multiple antennas spread across the Australian outback observe the same event simultaneously. The tiny differences in the arrival time of the signal at each separate dish are then combined, not unlike how your two ears work together to pinpoint the location of a sound. This allows astronomers to triangulate the origin of a fast radio burst with astonishing accuracy, narrowing it down from a vast celestial neighborhood to a specific cosmic address. This leap in localization was nothing short of transformative. Instead of a blurry, unresolved smudge on a star chart, astronomers could now point the Hubble Space Telescope, the Chandra X-ray Observatory, and other immense optical and infrared telescopes at a precise point in the sky and ask a simple, profound question: what is there? The answer, again and again, has been galaxies, but not just any galaxies. By identifying the host galaxy of a fast radio burst, scientists could immediately determine its exact distance by measuring the galaxy's redshift, confirming once and for all that these immense energies were indeed arriving from billions of light years away. This was the final, irrefutable proof of their extragalactic nature, but it was only the beginning of the story. The environments themselves became the next great clue. It turns out that not all galaxies are equal when it comes to hosting these mysterious events. The home galaxies of localized fast radio bursts have shown a fascinating and sometimes contradictory diversity. Some bursts originate from massive, ancient galaxies that are relatively quiet, where the primary stellar formation activity happened billions of years in the past. Others, however, have been traced back to dwarf galaxies, small and incredibly turbulent places that are currently undergoing massive bursts of star creation, forging new suns at a ferocious rate. This dichotomy is a vital piece of the puzzle. It suggests that while the engine that creates a fast radio burst might be the same type of object like a magnetar, the pathways to creating that engine could be very different. In a calm, old galaxy, the source might be the long-awaited finale of an ancient star's life, but in a frantic stellar nursery, it could be the violent birth cry of a new, immensely powerful object. Perhaps the most stunning localization achievement to date involved the first repeating burst, FRB 121102. After years of meticulous observation, astronomers were able to pinpoint its origin to a breathtakingly specific and unexpected location, a star-forming region within a dwarf galaxy over 3 billion light-years from Earth. This wasn't just somewhere in a galaxy, it was in the heart of the action, a chaotic and energetic nursery where massive stars are born and die in spectacular supernova. This precise environmental context strongly supports the leading theory that this repeater, and perhaps many like it, is powered by a magnetar. These incredibly dense, rapidly spinning neutron stars with magnetic fields 1,000 trillion times stronger than Earth's are exactly the kind of exotic object you would expect to find born in the aftermath of a supernova within such a violent stellar environment. The location provided the where, which in turn gave us our strongest hint yet about the what. While the evidence from distant galaxies was compelling, the true smoking gun in the case for magnetars arrived not from billions of light years away, but from our own cosmic backyard. For years, the leading theory pointed to these incredibly dense, spinning neutron stars with magnetic fields so powerful they could strip information from a credit card halfway to the moon. But a theory, no matter how elegant, requires direct observation to move from compelling idea to established fact. That moment arrived in April 2020, in what became arguably the most important event in the short history of fast radio burst science. Astronomers around the world watched in stunned amazement as a known object within our own Milky Way galaxy, a magnetar called SGR 1935+2154, suddenly roared to life. It had been known to science for years as a soft gamma repeater, a type of star known for occasional outbursts of high-energy gamma and X-ray radiation. But this time, it did something entirely different and unprecedented. As telescopes monitored this magnetar's latest period of activity, something extraordinary happened. Alongside its expected X-ray bursts, it unleashed a millisecond-long, incredibly intense flash of radio waves. This wasn't just a faint whisper, it was a full-throated shout detectable across the galaxy. The event was captured simultaneously by the Canadian CHIME telescope and the STRE-2 instrument in the United States, leaving no doubt about what they were witnessing. For the first time ever, a fast radio burst had been unambiguously linked to a specific known celestial object. The distance was no longer billions of light-years, but a mere 30,000 light-years away, right in our own galactic neighborhood. This changed everything. The proximity meant astronomers could study the aftermath and the environment in incredible detail, with a level of resolution completely impossible for distant extragalactic bursts. The characteristics of this galactic burst were the final piece of the puzzle. While its total energy was 1,000 times less than that of the extragalactic bursts seen from other galaxies, the profile was identical, a sharp, millisecond duration spike in the radio spectrum. This energy difference actually makes perfect sense. It confirmed that the engine is scalable. A magnetar in our galaxy doesn't need to be as powerful as one in a distant galaxy to still produce the same type of signature. This observation provided a crucial missing link, a nearby laboratory to test our models. It demonstrated that at least one type of fast radio burst is definitively produced by magnetars, solving a major part of the mystery. It proved that these extreme stellar remnants are capable of generating the specific conditions required to launch these incredibly brief, intensely energetic radio signals across the cosmos. But how does a magnetar actually create a fast radio burst? The process is as violent as it is fascinating. Imagine a star more massive than our Sun collapsing under its own gravity, crushing down into a sphere only about 12 miles across. This neutron star is born spinning rapidly and possessing a magnetic field of almost unimaginable strength. In the case of a magnetar, that magnetic field is so intense that it creates immense stress on the star's solid crust, which is harder than steel. Occasionally, this crust can fracture and shift in a starquake, an event of seismic proportions. This sudden disruption sends a massive wave of energy rippling through the magnetar's magnetosphere, a region dominated by its powerful magnetic field. This magnetic turmoil acts like a colossal particle accelerator, shaking free charged particles and generating a powerful shock wave that ripples outward at near light speed. It is this shock wave, plowing through the magnetized plasma surrounding the star, that is thought to generate the coherent, lighthouse-like beam of radio waves we detect as a fast radio burst. The detection from SGR 1935 plus 2154 didn't just confirm a source, it opened a new window into the diverse zoo of these cosmic events. It strongly suggests that there is a continuum of radio-bursting magnetar activity. On one end, we have the relatively weaker but more frequent radio bursts from galactic magnetars like this one. On the other extreme, we have the colossal, empire-striking, back-energy blasts from magnetars in distant galaxies. The difference in power could be due to the age of the magnetar, the strength of its magnetic field, or the specific environment it inhabits. This galactic event was the Rosetta Stone astronomers had been hoping for, providing a key to deciphering the far more powerful and distant signals. It confirmed that magnetars are indeed one of the universe's prime engines for these brilliant, mysterious flashes, turning a leading hypothesis into an observed, confirmed fact, and forever linking the fate of one class of fast radio bursts to the dramatic lives of these magnetic monsters. The incredible diversity in the homes of fast radio bursts provides perhaps our most crucial environmental clue. When we finally managed to pinpoint the exact galaxies these signals were coming from, we anticipated finding a pattern, a single type of cosmic neighborhood that would neatly explain their origin. Instead, we discovered a bewildering variety that initially seemed to complicate the mystery, but has ultimately offered a far richer understanding. These host galaxies range from tiny, chaotic dwarf galaxies to massive, serene elliptical giants, and each environment whispers something different about the possible engines powering these immense bursts. It appears the universe has more than one way to build a cosmic flashbulb. Consider the case of the first repeating burst, FRB 121102. Its home is a diminutive dwarf galaxy, a small, turbulent realm brimming with frenetic activity. This is not a quiet, settled place. It's a stellar nursery undergoing a massive burst of star formation, creating massive, short-lived stars that burn brightly and die young in spectacular supernova explosions. This chaotic environment is the perfect breeding ground for magnetars. The violent death of a massive star in such a region is exactly the kind of event that could leave behind a newborn, hyperactive neutron star with an unimaginably powerful magnetic field, capable of producing the repeated energetic outbursts we observe. The location fits the theory perfectly, like a key sliding into a lock. Yet, other fast radio bursts tell a completely different story. Some have been localized to massive, elliptical galaxies, ancient cities of stars that have largely finished their period of active star formation. These galaxies are dominated by older, redder stars and are relatively calm compared to their dwarf counterparts. The presence of FRB sources in these quiet giants was initially perplexing. If they aren't being born from the explosive deaths of young stars, then what is creating them? This points toward alternative, longer-term evolutionary pathways. Perhaps the source is an old magnetar that has been recently reactivated. maybe by accreting material from a binary companion star or by experiencing a delayed and catastrophic crustal shift after millennia of magnetic stress. It could even indicate an entirely different engine, such as the merger of two incredibly dense white dwarf stars, an event that can still occur long after a galaxy's primary period of star formation has ended. This stark contrast in galactic environments is a vital clue because it suggests that while the underlying physics of the burst itself might be similar, a sudden, coherent release of radio energy, the trigger mechanisms are diverse. The universe, it seems, has a menu of options for creating these phenomena. In a young, star-forming galaxy, the primary recipe might be the supernova-born Magnetar, fresh and highly active. In an older, more sedate galaxy, the trigger might be a rarer event, like the slow in-spiral and collision of two evolved stellar remnants. This doesn't simplify the mystery, but it deepens our appreciation for the complex life cycles of stars and the many ways a cosmos can announce itself across the void. The host galaxy, therefore, is not just an address. It's a biography telling us the life story of the region that gave birth to one of the universe's most brilliant and fleeting signals. This brings us to a particularly subtle but powerful clue hidden within the light itself, a characteristic that allows these signals to act as cosmic compasses charting magnetic fields across the universe. To understand this, we need to look at the concept of polarization. Imagine a regular radio wave traveling through the void, its electric field oscillating in all directions perpendicular to its path, like a jump rope being shaken in every possible up, down, and side-to-side motion. Now imagine that same wave being forced to oscillate in only one specific plane, say, strictly vertically or strictly horizontally. This ordered, disciplined vibration is what scientists call polarized light. It's a common phenomenon, but when observed in fast radio bursts, it becomes an incredibly sensitive probe of magnetic fields. The journey of a polarized radio burst is anything but straightforward. As it travels through magnetized plasma, whether near its source, in the interstellar medium of its host galaxy, or in the intergalactic voids between galaxies, its polarization becomes a recorded history of every magnetic field it has encountered. The most telling effect is a phenomenon known as Faraday rotation. This occurs when a polarized radio wave passes through a region containing free electrons and a magnetic field that has a component pointing along the wave's line of sight. This magnetic environment actually causes the plane of polarization to slowly rotate, like a dial being turned, as the wave propagates through it. The amount of this rotation depends on two key things: the strength of the magnetic field and the density of electrons it's moving through. The greater the combined effect, the more the wave's polarization plane twists before it reaches our telescopes. By meticulously measuring this rotation, calculating what's known as the rotation measure, astronomers can effectively take the cosmic fingerprint of the magnetic environment. For some fast radio bursts, the measured rotation measures are astoundingly high, orders of magnitude greater than anything we see within our own Milky Way. This was the case with the famous repeater FRB 121102, which exhibited an incredibly high rotation measure. This finding pointed directly to an origin within an environment stewing with a dense, magnetized plasma, such as the energetic nebula often surrounding a young Magnetar. The signal wasn't just telling us it came from a specific point. It was describing the intense magnetic maelstrom it had to fight its way out of, confirming the source was embedded in an extreme and dynamic region. The story gets even more intriguing when we look at how this polarization can change over time. For repeating sources, astronomers have been able to monitor the rotation measure across multiple bursts. In several cases, they've observed this value vary and even reverse sign between outbursts. This isn't a random fluctuation. It's a direct window into a dynamic, evolving environment around the central engine. A changing rotation measure suggests that the magnetic field along our line of sight is shifting. perhaps due to turbulent motions in the surrounding nebula or the precession or wobble of the Magnetar itself. A reversal of the sign is particularly profound, as it implies a literal reversal in the direction of the magnetic field the wave passed through. This level of detail transforms the fast radio burst from a simple flash into a sophisticated diagnostic tool, allowing us to map the invisible magnetic structures around some of the most exotic objects in the universe with a precision that was previously unimaginable. If the simple chirp of dispersion was the only pattern in these signals, the mystery might have been easier to solve, but nature, it seems, loves complexity. As our telescopes grew more sensitive and our data processing more refined, we began to see that many fast radio bursts are not just clean, single peaks of energy. Instead, they are intricate symphonies of emission composed of multiple smaller subbursts, each with its own fascinating internal structure. This complex frequency architecture is more than just a curiosity. It's a direct window into the violent physics happening at the source, a kind of seismic readout from the heart of a cosmic earthquake. One of the most common and telling patterns observed is what astronomers call downward frequency drifting. Picture a series of quick, distinct chirps that make up a single burst. With each successive chirp, you'll notice that the pitch starts at a slightly lower frequency than the one before it. It's as if a pianist were rapidly playing a scale, but with each new note beginning a half step lower than the last. This consistent downward drift across multiple subbursts is a massive clue. It strongly suggests that the origin point of each successive wave packet is physically moving outward through a region of rapidly decreasing plasma density. Imagine the blast wave from an explosion rippling outward through layers of a star's atmosphere. Each new layer it encounters has different properties, altering the character of the emission it produces. This drift pattern is the signature of a dynamic, expanding event, not a static one. This intricate structure points toward a specific type of emission mechanism known as coherent curvature radiation. To understand this, envision a clump of extremely energetic electrons caught in the incredibly powerful, twisted magnetic field lines near a magnetar. These electrons are forced to spiral along these curved field lines at nearly the speed of light. According to the fundamental laws of physics, any charged particle forced to follow a curved path must radiate energy, and when these electrons move in perfect, organized synchrony, a state called coherence, they can produce an intensely powerful, tightly beamed radio wave. The observed downward drift could then be explained by the radiating clump of electrons streaming outward along a field line that is itself curving away, causing each subsequent bit of radiation to be emitted from a slightly different location and at a slightly lower frequency. Another fascinating feature found in some bursts is band-limited emission. Unlike a typical radio signal that might span a wide range of frequencies, some fast radio bursts appear to be confined to a specific radio band, almost as if they were being transmitted on a particular cosmic radio station. This limitation is likely imposed by the environment surrounding the source. The signal might be generated across a broad range of frequencies, but as it tries to escape, it must pass through a shroud of dense magnetized plasma. This plasma acts like a filter, absorbing certain frequencies and only allowing a narrow band to pass through unscathed. The specific width and central frequency of this band can therefore tell us about the density and composition of this surrounding cocoon of material, providing yet another diagnostic tool to understand the source's immediate neighborhood. The time-frequency structure of these bursts is so rich with information that scientists have even begun to compare it to the sounds of earthly phenomena. The patterns of subbursts and their drift rates bear a striking resemblance to the seismic echoes following a tectonic earthquake or the descending tones of a percussive instrument like a xylophone. This isn't just a poetic comparison. It suggests that similar physical principles of shockwave propagation and resonance might be at play on a cosmic scale. By analyzing these patterns, astronomers can effectively perform seismology on a neutron star's crust or map the resonant cavities within its powerful magnetosphere, using the radio waves as their probe to understand conditions in a place where matter exists in states we cannot possibly recreate on Earth. For all their chaotic appearance, the universe often operates on hidden rhythms, and the search for these underlying cadences has become one of the most intriguing avenues in fast radio burst research. While some bursts appear to be completely random, firing off without any warning or pattern, others seem to whisper of a deeper, more orderly process at work. The hunt for periodicity, regular, repeating cycles in the bursting activity of these sources is like trying to discern the steady ticking of a cosmic clock beneath a torrent of static. Finding such a rhythm would be a monumental breakthrough, as it could directly point to the orbital mechanics or rotational dynamics of the source system itself, offering a clear physical model for what has until now been largely guesswork. The most famous candidate for this kind of behavior is the original repeater FRB 121102. After years of careful monitoring, a team of researchers analyzing its activity proposed a startling pattern, a possible cycle of approximately 157 days. According to their analysis, this source appeared to enter an active window, bursting frequently for about 90 days before falling silent for a subsequent 67-day period, then repeating the entire cycle. This wasn't a perfect metronome. The bursts within the active period were still stochastic, appearing at random times, but the overall on-off switch seemed to be governed by this long-term clockwork. If true, this periodicity immediately suggests an explanation rooted in orbital dynamics. Imagine a Magnetar in a long, eccentric orbit around another massive object, perhaps a companion star or a black hole. The active window could correspond to the period when the Magnetar is closest to its companion, a point called periastron, where gravitational forces or interactions with the companion's stellar wind might trigger heightened activity in the Magnetar's crust, leading to more frequent starquakes and bursts. However, the story of periodicity is filled with caution and complexity. The initial claim of a 157-day cycle for FRB 121102 was later challenged by additional data that didn't fit the pattern perfectly. This is a common challenge in astronomy, where observing schedules are finite and the universe is under no obligation to perform on a human timetable. Confirming a cycle requires years, sometimes decades, of consistent observation to distinguish a true astrophysical period from a random clustering of events that merely looks like a pattern, a phenomenon often called the clustering illusion. As more data on this repeater has rolled in, the picture has become fuzzier, with some studies supporting the original cycle and others suggesting it may have evolved or even dissipated over time. This doesn't necessarily invalidate the idea. It may instead reveal that these systems are not static. The orbital period could be precessing, or the internal engine of the Magnetar could be evolving, changing the observable bursting behavior over long timescales. Other repeating sources have added their own potential rhythms to the cosmic chorus. Another well-studied repeater, FRB 180916, was reported to exhibit a 16-day cycle, with 4 days of activity followed by 12 days of quiescence. This shorter, more frequent cycle points toward a different type of system altogether, perhaps one with a tighter orbital period or a different triggering mechanism. The variety of these proposed cycles, ranging from days to hundreds of days, powerfully indicates that we are not looking at a one-size-fits-all phenomenon. Instead, we are likely seeing a family of related sources whose specific bursting behavior is exquisitely sensitive to their individual circumstances, the strength of their magnetic fields, the nature of their binary companions if they have them, and the environment of plasma and dust that surrounds them. The pursuit of these patterns is more than just an academic exercise. It's a direct pathway to understanding the fundamental nature of these engines. A confirmed periodicity is a gift to theorists because it provides a crucial constraint for their models. It tells them the physical scale of the system. For an orbital period, Kepler's laws directly relate the period to the total mass of the system and the distance between the objects. This allows scientists to move from vague speculation to calculating specific numbers, building a precise picture of the binary system or the precessing neutron star that could be responsible. Even the absence of a clear period is informative, as it might steer us toward models involving more chaotic, one-off cataclysms or systems so complex that their rhythms are hidden beneath layers of unpredictable turbulence. Each tick of a potential cosmic clock, whether confirmed or debunked, brings us closer to telling time in the universe's most extreme and energetic regions. Now, to truly grasp the staggering nature of these events, we must confront their raw power, a clue written not in patterns or repetition, but in pure, unadulterated energy. The energetics and luminosity of fast radio bursts are what make them so utterly bewildering and force us to consider physics at its most extreme. When we say a burst releases more energy than our sun emits in 80 years, the number is so vast it becomes almost meaningless, an abstract figure that defies everyday comprehension. We need to break this down into a more relatable scale to appreciate the true violence of the event. Think of our sun. Every second, through the process of nuclear fusion in its core, it generates enough energy to power human civilization at its current rate for nearly 500,000 years. It is a constant titanic furnace that has burned steadily for over 4.5 billion years. Now, imagine taking all the energy that this vast engine produces over an entire day and compressing it. Not into a year, an hour, or even a second. Compress it into a single, fleeting millisecond, 1,000th of a second, a span of time so short that a hummingbird's wings beat 7 times within it. This is the scale of energy we are talking about for a single, garden-variety fast radio burst. It is an almost inconceivable concentration of power, a cosmic flashbulb of unimaginable intensity. But here is the critical distinction. This immense energy is not released in all directions like a bomb. If it were, the signal would be diluted across the vastness of space and we would likely never detect it. Instead, the energy is focused into an exceptionally tight, coherent beam, much like a lighthouse focusing its light into a narrow, rotating shaft that can be seen from far out at sea. This beaming is the key to the paradox. It means the total energy output of the source, while still enormous, is actually less than the mind-boggling figure we calculate when we detect the beam pointed directly at us. Astronomers estimate that the beaming angle is incredibly small, perhaps only a few degrees across. This focusing mechanism allows a powerful but not physically impossible engine to create a signal that appears impossibly bright from our privileged vantage point, as if we were looking directly down the barrel of the universe's most powerful spotlight. This incredible luminosity immediately rules out a vast number of potential sources. Ordinary stellar flares, even the most violent eruptions from our own sun, are simply not up to the task. They are thousands of times too weak. The collisions of average asteroids or comets are likewise dismissed as trivial firecrackers in comparison. The energy requirements point unequivocally to the most extreme objects and events in the cosmos. The gravitational energy released by the merger of 2 neutron stars or a neutron star and a black hole. The catastrophic release of magnetic energy stored in the twisted fields of a magnetar, or the accretion of matter onto a stellar mass black hole, where gravity can convert mass into energy. Unparalleled efficiency. These are the only known cosmic engines powerful enough to even be considered for the job. Furthermore, the fact that this energy is released predominantly in the radio part of the electromagnetic spectrum, and on such an infinitesimally short timescale, places incredibly tight constraints on the size of the emitting region. Whatever is happening, it must be happening fast. The source of the burst cannot be larger than the distance light can travel in that millisecond duration, which is about 300 kilometers. This immediately points to compact objects. We are not looking at the explosion of an entire star, which unfolds over hours or days. We are looking at an event happening on the surface of, or in the immediate vicinity of, an object no bigger than a small city, precisely the scale of a neutron star or a black hole's innermost accretion disk. The brevity of the burst is a direct measurement of the size of its engine, narrowing our search to the densest, most bizarre objects the universe has to offer. Yet another clue in our cosmic investigation comes not from the signal itself, but from what happens to it during its epic journey, a subtle smearing and shimmering effect that tells a profound story about the spaces between the stars. When a fast radio burst travels toward us, it doesn't move through a perfectly clear void. Instead, it must navigate a turbulent sea of tenuous plasma, a soup of free electrons that fills interstellar space within galaxies and the even more diffuse material in the vast voids between them. This plasma is not smooth, it's lumpy and turbulent with subtle density variations that act like countless tiny lenses scattered across space. As the coherent radio waves pass through this uneven medium, something fascinating happens. The path of each individual wave is minutely altered, a phenomenon known as scattering. The most visible effect of this scattering is a characteristic tail or smear that appears after the main pulse of the burst. Imagine a sharp, sudden clap of thunder in a large, empty arena. In a perfect environment, you'd hear one clean, crisp sound. But if the arena is filled with a complex arrangement of obstacles and reflectors, that single clap would be stretched into a prolonged echo, with the sound waves bouncing and taking multiple paths to reach your ears. In a very similar way, the turbulent interstellar plasma causes different parts of the radio wave to travel along slightly different paths. Some take a more direct route, while others get diverted and delayed, arriving at our telescopes a fraction of a second later. This creates a telltale scattering tail, a gradual, exponentially decaying fade-out following the initial sharp peak. The duration of this tail is a direct measurement of how much material the signal has encountered. A long, stretched-out tail indicates a journey through a very dense and turbulent environment, like the bustling core of a distant galaxy, while a short, crisp tail suggests a cleaner path through a more peaceful region. Beyond this temporal smearing, we also observe a captivating shimmering effect called scintillation. This is the astronomical equivalent of the twinkling of stars in our own night sky, which is caused by Earth's atmosphere blurring their light. For fast radio bursts, the scintillation occurs on a galactic and intergalactic scale. As the radio waves pass through the clumpy interstellar plasma, the waves interfere with each other, creating a pattern of bright and dark patches across different radio frequencies. The result is that the burst doesn't appear as a smooth signal. It looks like a complex, intricate tapestry of bright knots and voids in what's called the dynamic spectrum, a plot of intensity versus both time and radio frequency. This scintillation pattern is not just random noise. It's a unique fingerprint of the specific turbulent screens of plasma the signal passed through on its way to us. By analyzing this pattern, astronomers can perform a technique called scintillation arc analysis. It's a bit of cosmic detective work where they use the intricate frequency structure to reconstruct the properties of the intervening material. The scale and shape of the scintillation can reveal the relative velocity of the scattering material, its distance from the source, and the typical size of the plasma density fluctuations. For a repeater, we can even watch how the scintillation pattern changes from burst to burst. If the pattern remains stable, it suggests the scattering is happening very close to the source, within its own host galaxy or even in its immediate nebula. If the pattern changes rapidly, it points to scattering screens much closer to us within the Milky Way. This allows scientists to effectively peel apart the different layers of the cosmic onion, separating the influence of our own galaxy's interstellar medium from that of the host galaxy and the intergalactic space in between. Each scattered echo and each shimmering pattern in the signal is therefore a detailed report on the invisible structure of the universe, turning a mysterious flash into a precision tool for mapping the cosmos's most diffuse and elusive material. This pursuit of multi-wavelength light is one of the most critical races in modern astronomy, a frantic sprint to catch a fleeting cosmic event in every possible color of the energy spectrum. When a fast radio burst alert flashes across astronomers' computer screens, it triggers an immediate and coordinated global response. Optical telescopes swivel toward the coordinates, X-ray observatories like Swift and Chandra lock on, and gamma-ray detectors scan the skies, all hoping to capture a simultaneous flash of light at other wavelengths. The presence or absence of these counterparts is not just a minor detail. It is a fundamental clue that can instantly validate or completely dismantle our theories about what powers these immense explosions of radio waves. Imagine a catastrophic event like two neutron stars colliding. Such a merger would not just be a silent affair in radio waves, it would be a multi-sensory cosmic firework, unleashing a torrent of energy across the entire electromagnetic spectrum. We would expect to see a brilliant optical afterglow, a burst of high-energy X-rays, and a signature flash of gamma rays, the most energetic form of light. This is precisely what astronomers observed in 2017 with the neutron star merger event known as GW170817. That event was a textbook example of a multi-messenger phenomenon, detected in gravitational waves, gamma rays, and optical light. If a fast radio burst were produced by a similar cataclysm, it should come packaged with this entire energetic ensemble. Yet, for the vast majority of bursts, the search for these accompanying signals has come up empty. This profound silence is in itself one of the most telling results. The absence of significant gamma-ray or X-ray emission immediately rules out the most violently explosive one-off events for most fast radio bursts, steering us away from models involving superluminous supernova or massive black hole births, and instead pointing toward more focused, engine-driven processes. There are, however, monumental exceptions that prove the rule and fundamentally shape our understanding. The most spectacular example is the galactic fast radio burst from the Magnetar SGR 1935 plus 2154 in 2020. This event was a breakthrough precisely because it was not a lonely radio shout. It was accompanied by a powerful simultaneous X-ray burst. This dual detection was the smoking gun that firmly linked at least one type of fast radio burst to Magnetar activity. It demonstrated that the same starquake or magnetic upheaval that shook the neutron star's crust could produce emission across multiple wavelengths. The X-rays likely came from the immediate fireball of hot plasma at the surface, while the radio waves were generated by particles accelerating in the magnetosphere above. This multi-wavelength fingerprint provides a template for what we should look for in distant extragalactic magnetars, giving us a specific set of characteristics to hunt for in the data. For the repeating fast radio bursts, the search for counterparts has taken a more patient, watchful approach. Instead of a mad dash to catch a single event, astronomers can point their most powerful telescopes at a known repeater and simply wait, gathering data across the spectrum during both its quiet periods and its active, bursting states. This strategy has yielded intriguing hints. In 2019, observations of the famous repeater FRB 121102 with the immense Arecibo telescope and the Gemini optical telescope revealed something remarkable: a faint, persistent radio source coincident with the burst's location, alongside a faint, flickering optical counterpart. This suggested the repeater might be embedded within a persistent nebula of energetic particles, a nebula powered by the young, hyperactive Magnetar. The bursts themselves might be just the brightest eruptions from an object that is constantly churning and emitting at a lower level across different energies, painting a picture of a dynamic, complex environment rather than a simple one-off explosion. The continued absence of strong, consistent counterparts for most one-off bursts powerfully constrains their possible origins. It suggests an emission mechanism that is incredibly efficient at producing radio waves, but remarkably inefficient at producing other forms of light. This is a hallmark of coherent emission processes, like the curvature radiation we discussed earlier, where particles act in unison to produce a brilliant, tightly beamed radio flash without necessarily heating their surroundings to the extreme temperatures needed to generate copious X-rays or gamma rays. Each non-detection in another wavelength narrows the field of possible suspects, forcing theorists to refine their models and focus on mechanisms that can deliver an immense amount of power exclusively into a specific radio channel, leaving the rest of the cosmic spectrum dark and silent. This great multi-wavelength hunt, therefore, continues to serve as our most effective filter, separating speculative ideas from physically plausible engines for the universe's most brilliant and enigmatic flashes. This growing catalogue of hundreds of detected events has itself become a powerful scientific instrument, allowing us to step back from individual mysteries and analyze the population as a whole. Think of it like this: studying one human tells you about a specific person, but studying demographics across an entire country reveals patterns about health, behavior, and life expectancy that you could never see up close. In the same way, by compiling the properties of every recorded fast radio burst, their dispersion measures, their energies, their durations, and whether they repeat, we can begin to see the overarching rules that govern this entire cosmic population. This statistical approach moves us from asking what was that to asking what are they in general. One of the most profound revelations from this big data approach is the sheer event rate happening across the cosmos. Current estimates suggest that a fast radio burst goes off somewhere in the observable universe roughly 1,000 times every single day. That's about one every minute and a half. This staggering frequency tells us that whatever is producing them is not an incredibly rare, once-in-a-generation event like the merger of two black holes. Instead, these sources must be common, and the physical mechanism behind them must be a routine, if violent, process in the life cycle of certain celestial objects. The universe is crackling with this activity. We're only just now tuning our instruments to hear the constant chorus. Delving into the statistics also strongly suggests that we are not dealing with a single, monolithic phenomenon. The data reveals a clear and telling dichotomy between one-off bursts and repeating sources. Repeaters, like the famous FRB 121102, make up a small but significant minority, perhaps around 20% of all known sources. They tend to be slightly less energetic on average than the single, colossal blasts, and often show more complex time-frequency structures with multiple sub-bursts. The one-off events, by contrast, are the true titans. They unleash their entire energy budget in a single, catastrophic millisecond flash and are never heard from again. This fundamental split in behavior is the strongest evidence we have for at least two distinct formation channels operating in the universe. This leads to the compelling concept of a fast radio burst zoo, much like the variety we see with supernova. We know there are type Ia supernova from white dwarf explosions and type II supernova from massive star collapses. They have different triggers and different observational signatures, but they are both ultimately stellar explosions. The population data suggests a similar taxonomy is emerging for fast radio bursts. One class, likely the repeaters, could be tied to the persistent and recurring activity of young, hyperactive magnetars. The other class, the one-off events, might be the final, desperate death cry of an object, such as the cataclysmic collapse of an overly massive neutron star into a black hole or the instantaneous annihilation of a magnetar's super-strong magnetic field in what's called a magnetic avalanche. Furthermore, the distribution of dispersion measures across the population paints a rough map of where these events are occurring throughout cosmic history. The catalog contains bursts with a wide range of dispersion measures, indicating sources at many different distances. This tells us that fast radio bursts have not only been happening in the modern universe but have been occurring for billions of years. We are detecting signals that were generated when the universe was half its current age, meaning the conditions to create them have existed for a significant portion of cosmic time. This longevity rules out explanations that rely on conditions only present in the very early or very late universe, anchoring these events as a persistent feature of an evolving cosmos. By counting them and charting their distances, we are effectively taking a census of the most violent and energetic events across time and space, using statistics to write the natural history of the universe's most brilliant flashes. For all the mystery surrounding individual bursts, perhaps the greatest leap forward in our understanding came not from studying one in isolation, but from finally seeing them by the thousands. This statistical revolution was made possible by a single, groundbreaking instrument that fundamentally changed the scale of the entire field: the Canadian Hydrogen Intensity Mapping Experiment, known to everyone simply as CHIME. Unlike the massive, steerable dishes like Arecibo or Parkes, CHIME is an entirely different kind of telescope. It's a stationary array composed of 4 half-pipe-shaped cylinders, each as long as a football field, equipped with over 1,000 radio receptors. Its design isn't for staring intently at one tiny patch of sky. It's for hearing everything happening across the entire northern hemisphere at once. While its original mission was to map the vast cosmic web by detecting hydrogen gas, its true, world-altering legacy would be written in the language of fast radio bursts. CHIME power lies in its immense field of view and its ability to process a tsunami of data in real time. Every day, as the Earth rotates, this fixed array sways its gaze across an enormous swath of the sky. It's like having a security camera that monitors an entire city block instead of a single doorway. You're far more likely to catch a fleeting event, but seeing the event is only half the battle. The real magic happens in the supercomputer-powered brain of the telescope. The raw data stream from all those antennas is a flood of information that would be impossible for humans to sift through. CHIME automated systems are constantly analyzing this deluge, running sophisticated algorithms trained to recognize the unique fingerprint of a fast radio burst, that telltale sweep of dispersion, in real time, plucking these cosmic needles from a mountainous haystack of radio noise. The impact was immediate and staggering. Before CHIME came online in full force around 2018, the entire world's catalog of fast radio bursts numbered in the dozens, each one a precious, hard-won discovery. Within its first year of operation, CHIME had multiplied that number by a factor of 10, then 100. To date, it has detected thousands of events, single-handedly transforming these enigmatic signals from rare curiosities into a common celestial population. This wasn't just an incremental increase, it was a paradigm shift. For the first time, scientists had a dataset so large they could stop asking what is this one thing and start asking what are these things as a whole. They could finally do statistics, and statistics have a power to reveal truths that the study of individual anomalies simply cannot. This fire hose of new data allowed astronomers to build the first robust distributions of key properties. They could create a histogram of dispersion measures which confirmed that these bursts were coming from all across cosmic time, from relatively nearby to the very edges of the observable universe. They could plot the distribution of energies, revealing a continuous spectrum that suggested a common engine could be scaled to produce both the faintest and the most brilliant events. They mapped the sky locations, showing that fast radio bursts are not concentrated in any particular direction, but are isotropically distributed, meaning they fill the entire universe fairly evenly. This last point was a crucial nail in the coffin for any remaining theories that they might be some strange local phenomenon within our own galaxy. The sources were truly cosmological everywhere we looked. Perhaps CHIME's most profound contribution has been its role in dramatically expanding the known population of repeating fast radio bursts. Before its reign, only a handful of repeaters were known, making them fascinating outliers. CHIME has since uncovered dozens of repeating sources, proving that repetition is not a rare fluke but a common behavior for a significant fraction of these objects. This wealth of new repeaters allowed for direct apples-to-apples comparisons. Scientists could see that while all repeaters share the trait of firing multiple times, their personalities are wildly different. Some, like the original 121102, are hyperactive and prolific. Others are much more subdued, firing off a burst only every few months. Some show clear downward drifting subbursts, while others are simpler. This diversity strongly suggests that even within the class of repeating engines, there is a spectrum of activity, likely influenced by the age of the magnetar, the strength of its magnetic field, and the density of the environment that surrounds it. By providing this vast library of bursts, CHIME handed theorists the raw materials they desperately needed to test their models against reality. A model that could explain one or two strange events might just be a clever story, but a model that could accurately predict the statistical properties of thousands of bursts across the sky is likely touching on something true. The data validated some ideas and ruthlessly discarded others, forcing a rapid and healthy evolution in our understanding. The CHIME revolution taught us that to truly decode the mystery of fast radio bursts, we couldn't just wait for the perfect singular event. We needed to listen to the universe's entire chorus, and in doing so, we began to hear the underlying music for the very first time. This journey through the turbulent interstellar medium brings us to one of the most mind-bending and revealing clues of all. The fact that the material that smears and scatters these signals can also, under the right conditions, act as a colossal cosmic magnifying glass. We've seen how plasma clouds can distort a fast radio burst, but what if that distortion could actually make the signal temporarily brighter or even split it into multiple copies? This isn't science fiction, it's a real gravitational lensing effect, but with a fascinating twist. Instead of the warping of space-time by a massive object like a galaxy, this is plasma lensing, where a dense cloud of free electrons can focus radio waves, creating effects that are just as dramatic and infinitely more informative. To understand how this works, imagine a simple glass lens. Its curved shape bends light rays, bringing them to a focus and making whatever you're looking at appear larger and brighter. Now replace that glass with a cloud of magnetized, turbulent plasma. As a fast radio burst travels through this cloud, the radio waves interact with the free electrons. The key is that the density of this cloud isn't uniform. It has a gradient, being denser in the center and thinner toward the edges. This density gradient acts like a curved surface, causing the radio waves to bend inward, just like light bending when it enters water. If the geometry is just right, if the cloud is positioned perfectly between us and the source, this bending can cause the waves to converge, focusing them and resulting in a spectacular, temporary amplification of the signal. We see a burst that is orders of magnitude brighter than it would be otherwise, all because of a perfectly placed cosmic lens we didn't even know was there. The signatures of this lensing are unmistakable and utterly captivating. One of the most telling signs is the appearance of multiple images. Just as a funhouse mirror can create several warped reflections, a complex plasma lens can split the single signal from a fast radio burst into two or more distinct copies. Because each copy takes a slightly different path through the lens, they arrive at our telescopes at minutely different times, perhaps separated by mere milliseconds. This creates a unique echo effect within the burst structure itself. Another signature is an extreme, rapid brightening followed by an equally rapid fading as the relative motion between the source, the lens, and our line of sight moves in and out of that perfect focal alignment. The most dramatic fingerprint, however, is a strong frequency dependence. the focusing power of a plasma lens is much more effective at lower radio frequencies. This means you might see a burst appear incredibly bright at low frequencies while being completely undetectable at higher ones, a telltale clue that you're witnessing a lensing event rather than the intrinsic brightness of the source itself. For astronomers, catching a lensed fast radio burst is like hitting the scientific jackpot because it transforms a mysterious flash into a precision diagnostic tool. By carefully analyzing the properties of the multiple images or the amplification curve, the specific way the signal brightens and fades, scientists can perform a kind of cosmic tomography. They can reconstruct the detailed structure of the invisible plasma cloud itself, mapping its density fluctuations, its size, and even its shape. This is a direct way to study the fine-scale structure of the otherwise elusive material that floats in the halos of galaxies or in the vast filaments of the cosmic web. Furthermore, the lensing effect can provide an independent and highly precise measurement of the source's size. The amount of amplification is sensitive to how point-like the source is. If it's too large, the lensing effect gets washed out. By measuring the brightening, we can constrain the size of the emitting region to be less than about 10 kilometers across, which is exactly the scale of a neutron star, providing yet more compelling evidence for magnetars as the engines behind these events. Perhaps the most profound implication of plasma lensing is its ability to resolve a long-standing paradox, the apparent impossibility of some bursts. We've detected a handful of fast radio bursts with calculated energies so stupendously high that they strain the limits of known physics, even for magnetars. They seem to require energies that would tear apart the very star supposed to be producing them. Plasma lensing offers an elegant solution to this energy crisis. What if these apparently super-energetic bursts aren't actually that powerful intrinsically? What if they are just ordinary bursts that have been dramatically amplified by a fortuitous plasma lens situated somewhere along their path? The lens acts like a cosmic amplifier, taking a signal that would have been relatively faint and boosting it to an intensity that makes it appear impossibly powerful. This doesn't diminish the mystery, it refines it. It means we must now be brilliant detectives, separating the true nature of the source from the distorting effects of its journey. And in doing so, we uncover not one hidden truth, but two: the nature of the burst itself and the structure of the invisible material that helped reveal it. Yet these fleeting signals force us to confront the very limits of matter itself, pushing our understanding of how particles behave under conditions we can scarcely replicate on Earth. The plasma surrounding a neutron star isn't a simple gas. It's a state of matter so dominated by magnetic forces that it behaves unlike anything we know. In these environments, the magnetic field is so powerful it can actually twist the vacuum of space itself, a phenomenon predicted by quantum electrodynamics. This isn't just a theoretical curiosity, it has direct consequences for how radio waves are generated and propagate. The radio emission we detect must navigate this bizarre, magnetically saturated plasma, and its ability to escape at all tells us that the plasma must have a very specific and likely very low density. If it were too dense, the radio waves would be absorbed or scattered into oblivion long before they could break free. The very existence of a clear, detectable fast radio burst implies that the magnetar's magnetosphere possesses just the right conditions, a Goldilocks zone of plasma density, that allows these immense energies to be beamed outward into the universe instead of being trapped forever near the star's surface. Furthermore, the incredible brightness temperatures calculated for these bursts, often exceeding 10 to the 35 Kelvin, defy conventional physics. A temperature that high implies particles moving with unimaginable energy, but it's a misleading term in this context. This isn't thermal heat, it's a signature of a coherent process where vast numbers of electrons are radiating in perfect unison, like a colossal laser operating at radio frequencies. The only known mechanism that can achieve this coherence in such a hostile environment is something called bunched emission or maser activity. This requires a population of electrons with a very specific energy distribution, what's known as an inverted population, where more electrons are at higher energy states than lower ones, creating a situation ripe for an avalanche of stimulated emission. The fact that we see this coherence tells us that the magnetic field must be not only strong but also incredibly well ordered, capable of organizing these particles into a synchronized swarm that can release its energy in a single directed shot. The millisecond duration of the burst then acts as a stopwatch, telling us that this entire process from trigger to emission must unfold with breathtaking speed and precision, all within the rigid constraints imposed by the most powerful magnetic fields in the known universe. But perhaps the most revolutionary application of these signals lies in their potential to finally account for the universe's so-called missing baryons. For decades, cosmologists have faced a puzzling discrepancy. When they tally up all the normal matter, the protons and neutrons, also known as baryons, that was created in the Big Bang, and then compare it to the amount we can actually see in stars, galaxies, and detectable gas, a huge portion, nearly half, is unaccounted for. This isn't dark matter, it's the regular stuff we're made of that seems to have vanished. The leading theory posits that these missing baryons aren't in any dense, visible form, but are instead spread throughout the vast, empty spaces between galaxies in a diffuse, million-degree web of thin, ionized gas known as the warm-hot intergalactic medium, or WHIM. This gas is so incredibly tenuous and so hot that it doesn't emit detectable light, making it virtually invisible to our traditional telescopes. This is where fast radio bursts become the perfect tool for the job. Each burst, with its precisely measured dispersion, is effectively a direct probe of the total number of free electrons along its entire line of sight. By carefully subtracting the known contributions from our own Milky Way's interstellar medium, and when possible, the interstellar medium of the host galaxy, astronomers are left with the dispersion caused solely by the intergalactic medium, the stuff between the galaxies. This gives us a direct measurement of the total amount of ionized gas the signal traveled through. By analyzing bursts coming from many different distances and directions, scientists can begin to build a three-dimensional map of this elusive material. The early results are spectacularly promising. The dispersion measures from localized bursts align almost perfectly with predictions for the amount of material in the cosmic web, providing the first strong observational evidence that the missing baryons have been hiding in this warm-hot intergalactic medium all along. Each new burst is like a single pixel in a vast, emerging picture, slowly revealing the invisible skeleton upon which the entire visible universe is built. Beyond simply mapping matter, fast radio bursts also offer a unique laboratory for testing the very fabric of reality itself. One of the most fundamental tenets of modern physics is that all massless particles, including photons of light and radio waves, travel at the same speed in a vacuum, the speed of light denoted by c. This is a cornerstone of Einstein's theory of relativity. However, some theories of quantum gravity, which attempt to unify general relativity with quantum mechanics, suggest that this might not be perfectly true at extremely high energies. They propose that the vacuum of space itself might have a subtle, granular structure at the tiniest possible scales, and this could cause very high-energy photons to travel at a slightly different speed than their lower-energy counterparts. For most astronomical observations, this effect would be infinitesimally small, completely drowned out by other phenomena. But a fast radio burst, which travels billions of light years and covers a huge range of radio frequencies, could amplify this tiny effect into something detectable. The test is beautifully simple in concept. We look for any deviation from the perfect, smooth dispersion curve we expect from the interaction with free electrons alone. If a higher energy radio wave from a distant burst arrived at a measurably different time than a lower energy wave from the same burst, a time delay that couldn't be explained by the plasma dispersion, it could be the first hint of this quantum graininess of space-time. While no such signal has been definitively found yet, the mere act of looking pushes the boundaries of fundamental physics. Each new, exceptionally bright burst from the distant universe provides a more sensitive test, allowing us to place ever more stringent limits on these exotic theories. In this way, these cosmic messengers are not just helping us map the universe, they are helping us test the rules that govern it, probing for cracks in our understanding that could lead to the next great revolution in physics. Now, let's venture into the complex gravitational dances that might orchestrate some of these cosmic explosions, turning our attention to theories involving binary systems. While the solitary Magnetar is a compelling engine, the universe loves a good partnership, and many of its most energetic phenomena arise from the intimate and often violent tango between two massive objects. Imagine a neutron star, itself the remnant of a supernova, locked in orbit with another star or perhaps even a black hole. This isn't a peaceful coexistence. It's a relationship defined by extreme gravity, tidal forces, and a constant exchange of matter and energy, creating a perfect breeding ground for the kind of catastrophic instability that could launch a fast radio burst. One of the most plausible scenarios in this binary ballet involves accretion. Picture a neutron star with a companion, a more typical star that has swelled into a red giant. The immense gravity of the ultra-dense neutron star begins to violently strip material from its larger partner. This stolen gas doesn't fall directly onto the neutron star. Instead, it forms a swirling, superheated disk of plasma, an accretion disk that spirals inward. As this material piles onto the neutron star's magnetic poles, it creates immense pressure and heat, triggering powerful thermonuclear explosions on the surface. These bursts of energy could suddenly dump a massive amount of energy into the star's magnetosphere, shocking the surrounding plasma and triggering the coherent radio emission we see as a fast radio burst. In this model, the binary companion acts as a fuel source, periodically feeding the neutron star just enough to cause a spectacular outburst. The orbital dynamics of such a system could also elegantly explain the tantalizing periodicities we observe in some repeaters. The proposed 157-day cycle of FRB 121102 fits beautifully into this framework. If the neutron star is in a highly elliptical orbit, its activity would be heavily influenced by its proximity to its companion. During the part of its orbit where it swings closest periastron, the gravitational and tidal stresses would be at their maximum. This could compress the Magnetar's crust, triggering more frequent starquakes, or it could dramatically increase the rate of accretion, pouring more fuel onto the fire. As the neutron star moves away to the farthest point of its orbit, these triggers would subside and the source would enter a quiet phase. The orbit itself becomes the master clock, regulating the activity of the burst. But the possibilities get even more extreme. Consider a binary system where both objects are neutron stars, slowly spiraling toward each other over millions of years. In the final moments before their cataclysmic merger, their incredibly powerful magnetic fields could become entangled and reconfigured in a phenomenon known as a magnetospheric interaction. As they draw closer, their magnetic fields would snap and reconnect, launching enormous shocks through the surrounding plasma. This could potentially generate a brilliant, one-off fast radio burst just milliseconds before the two stars collide to form a black hole, a final, desperate signal sent out just as the system destroys itself. This would neatly explain why we never hear from that particular source again. The presence of a binary companion also helps solve some perplexing environmental puzzles. Remember the diversity of host galaxies. A binary system provides a versatile engine that can operate in both young and old stellar neighborhoods. In a young, star-forming galaxy, the companion could be a massive star, and the resulting fast radio burst would be a birth cry from a new magnetar being fed by its sibling. In an ancient, quiet galaxy, the binary could consist of two evolved stellar remnants, a neutron star and a white dwarf, for instance, in a long, slow dance. Here, the trigger might be sporadic and much rarer, occurring only when instabilities in the accretion disk cause a sudden avalanche of material to crash onto the neutron star's surface. This single model, with slight variations, can therefore explain bursts across cosmic time, making binary systems one of the most adaptable and powerful theories in our quest to decode these brilliant cosmic enigmas. This connection to the violent deaths of stars leads us to one of the most compelling environmental clues discovered so far: the observed association between some fast radio burst sources and the chaotic, expanding shells of material left behind by supernova explosions. When a massive star reaches the end of its life and explodes as a supernova, it doesn't just vanish. It leaves behind a rapidly expanding cloud of energized gas and dust, along with a dense stellar corpse at its center. For years, astronomers have theorized that these turbulent remnants could be the perfect breeding grounds for the magnetars thought to power many fast radio bursts, and recent localizations have provided stunning confirmation, placing several repeaters directly inside these cosmic wreckage fields. The link makes perfect physical sense. A core collapse supernova, the explosion of a star at least 8 times more massive than our Sun, is one of the most violent events in the universe. In that cataclysm, the star's outer layers are blasted into space while its core collapses under immense gravity. If the core is between about 1 and 3 solar masses, it doesn't form a black hole but instead crushes down into a city-sized neutron star, spinning rapidly and possessing a magnetic field of unimaginable strength. In the moments after the explosion, this newborn neutron star can be kicked by asymmetrical forces, receiving a powerful natal kick that sends it speeding away from the supernova's epicenter at hundreds of kilometers per second. However, it takes time for the star to outrun its own aftermath. For thousands of years, the magnetar and the supernova remnant coexist, with the young neutron star residing inside the expanding bubble of its own birth cloud. This environment is anything but peaceful. The supernova remnant is a maelstrom of shock waves, reverse shocks, and turbulent magnetized plasma. It is filled with the very free electrons that we know can scatter and affect radio waves. For a young magnetar at the heart of this storm, the conditions are ideal for producing the kind of activity we see in repeating fast radio bursts. The external pressure from the surrounding remnant can confine the magnetar's own energetic wind of particles, creating a standing shock front that acts like a buffer zone. This confined, high-pressure environment might be crucial for facilitating the coherent radio emission process, effectively providing the walls of the chamber needed to focus the explosion. Furthermore, the dense shell of the remnant could act as the persistent radio source, observed coincident with some repeaters, a nebula glowing from the continuous injection of energy by the central spinning magnetar. The most famous example of this association is once again the original repeater, FRB 121102. Precise localization tied it not just to a dwarf galaxy, but to a very specific region within that galaxy that is brimming with the telltale signs of recent star formation and stellar death. While a definitive shell-like supernova remnant hasn't been resolved around it, the source is embedded in a persistent, compact nebula that is exactly what astronomers would expect to find around a very young magnetar still inside its birth cloud. This nebula is likely a magnetar wind nebula, powered by the relativistic wind of particles flowing from the spinning neutron star, and it is being constantly stirred and energized by the same processes that generate the burst. This provides a natural explanation for the extreme magnetic field strengths inferred from the signal's Faraday rotation. The magnetar is essentially firing its bursts through the incredibly dense and magnetized plasma of its own making. Other repeating sources have shown an even more direct link. FRB 180916 was localized to the outskirts of a massive spiral galaxy, and its line of sight traces back to a region that shows clear signs of a recent massive star formation event. Similarly, FRB 1905203 was found to be coincident with a globular cluster in the galaxy M81. Globular clusters are dense collections of very old stars, which was initially surprising, but it suggests an alternative formation path. The Magnetar could have been formed not from a recent massive star explosion, but from the merger of two white dwarfs or other compact objects in the dense cluster environment, which then produced a faint supernova-like transient, leaving behind a magnet and a small remnant. This diversity shows that while the supernova remnant connection is a powerful and prevalent model, the universe may have several ways to create the turbulent, magnetized nurseries required to host these phenomenal cosmic engines. This growing collection of data points is where we find our next major clue, lying not within any single spectacular burst but in the quiet patterns emerging from the crowd. The true power of any scientific investigation often reveals itself not in the lone anomaly, but in the aggregate, and for fast radio bursts, this has meant the meticulous construction of comprehensive catalogs and databases. Think of each individual detection as a single witness to a crime. Their story might be compelling, but it's also unique and potentially biased. Now, imagine assembling 100 or 1,000 witnesses. Suddenly, the consistent patterns in their testimonies become the undeniable truth, while the outliers and contradictions point toward more complex, hidden realities. This is the transformative power of the FRB catalog. It turns a series of fascinating anecdotes into a robust body of statistical evidence. The creation of these databases is a monumental international effort, a symphony of data flowing in from the world's great observatories. Instruments like CHIME in Canada, ASKAP in Australia, FAST in China, and the venerable Arecibo dish in Puerto Rico before its collapse all contribute their unique findings. Each telescope has its own strengths. CHIME provides the immense volume, ASKAP offers unparalleled precision in localization, and FAST delivers incredible sensitivity to fainter signals. The challenge and the triumph lies in standardizing this flood of information. Scientists must carefully calibrate and homogenize the data, accounting for each telescope's specific characteristics, sensitivities, and observational biases to create a unified and trustworthy resource. This process ensures that a burst detected by CHIME can be meaningfully compared to one found by ASKAP, allowing researchers to see the forest for the trees and identify universal properties that govern the entire population. Once assembled, these catalogs become playgrounds for discovery through a process known as population studies. With hundreds of events at their fingertips, astronomers can generate histograms and distribution plots for every conceivable property: dispersion measure, rotation measure, temporal width, spectral bandwidth, peak luminosity, and total energy. The shapes of these distributions are incredibly revealing. For instance, the distribution of dispersion measures paints a rough map of the universe's matter content, showing us how many bursts originate from nearby and how many come from the deep cosmos. The energy distribution often reveals a clear break or turnover, separating the more common, less energetic events from the rarer, ultra-powerful monsters, suggesting there might be two distinct physical mechanisms or source classes at work. These databases are also essential for hunting the subtle correlations that whisper of underlying physical processes. Is there a relationship between a burst's width and its distance? Do bursts with higher rotation measures, indicating stronger magnetic environments, also show more complex time-frequency structures? Does a repeater's activity level correlate with the star formation rate of its host galaxy? By querying the catalog with these questions, scientists can move beyond speculation and uncover the genuine, statistically significant links that connect the observable properties of these bursts to the physics of their sources. A strong correlation can instantly validate a theoretical model, while a surprising absence of correlation can force a complete rethink of established ideas. Perhaps one of the most valuable functions of a large catalog is its ability to confidently identify the true anomalies, the events that stand so far outside the norm that they demand a unique explanation. Every population has its outliers, and in science, these outliers are not nuisances to be discarded. They are often the most important discoveries, pointing toward new phenomena previously hidden within the noise. A comprehensive catalog allows researchers to set precise statistical thresholds to identify these rare events automatically. Is there a burst with an impossibly high dispersion measure, suggesting it may have traveled through an unusually dense region of the cosmic web? Is there a repeater whose activity cycle is an order of magnitude longer than any other, hinting at a binary system with a vast orbital separation? These unique specimens become immediate targets for intense, focused follow-up, as understanding why they break the rules can often teach us more about the rules themselves. In this way, the collective power of the catalog doesn't just help us understand the average. It actively guides us toward the exceptional, ensuring that no cosmic secret, no matter how well hidden, remains buried for long. Now we venture into the heart of the engine room itself to explore the microscopic physics that could actually generate these immense flashes. Our next clue lies in the role of plasma instabilities. To understand this, we must first appreciate the environment we're dealing with. The region around a magnetar isn't just empty space. It's a seething, turbulent soup of plasma, a state of matter where atoms have been torn apart into a superheated gas of free electrons and ions. This plasma is so utterly dominated by the neutron star's unimaginably powerful magnetic field that it doesn't behave like any gas we know on Earth. It's forced to move along the magnetic field lines, creating conditions ripe for some of the most extreme and energetic physics in the universe. Within this magnetized maelstrom, even a small disturbance can trigger a runaway chain reaction known as a plasma instability. Think of it like this. If you carefully pour cream into a cup of coffee, you might create a stable, layered system for a moment. But give it the slightest stir, and that stability breaks down into a chaotic, swirling pattern of vortices that rapidly mix the two fluids. Around a magnetar, the stirring is constant and violent, caused by starquakes, magnetic field reconnections, or sudden injections of energy. This can push the plasma into a state that is wildly out of equilibrium, and nature abhors an imbalance. The plasma must find a way to release this pent-up energy, and it often does so not in a smooth flow, but in a sudden, catastrophic instability that can dump enormous energy into accelerating particles to near light speed. One of the most promising theories for generating the coherent radio emission we see involves a specific type of instability that creates what's called a two-stream or bunching instability. Imagine two clouds of electrons moving through the magnetosphere at different speeds. The faster cloud can actually overtake the slower one, and as they interact, the faster electrons begin to transfer energy to the slower ones. This doesn't happen smoothly. Instead, it causes the electrons to clump together into tightly packed, organized groups or bunches. This is the critical step. When charged particles are moving in sync like this, they can radiate energy in phase with one another, a process known as coherent emission. It's the difference between a crowd of people clapping randomly, which produces a dull roar, and the same crowd clapping in perfect unison, which creates a powerful, focused sound. The plasma instability provides the conductor that orchestrates this perfect synchronization, transforming the random motion of particles into a unified, colossal shout in the radio spectrum. Another compelling process involves instabilities within powerful relativistic shocks. Picture a blast wave from a Magnetar quake plowing through the surrounding magnetosphere at 99% the speed of light. This shock front is a site of incredible violence where magnetic fields are tangled and compressed and particles are slammed into one another. Instabilities can rapidly grow along the surface of this shock, creating intricate structures and whirlpools of plasma. These turbulent regions act like natural particle accelerators, far more powerful than any built on Earth. Electrons caught in these vortices are whipped around in curved paths by the magnetic fields, and as they do, they radiate energy. If the conditions are just right, an instability can force a vast number of these electrons to radiate at the same frequency and in the same phase, again creating that all-important coherent burst. The millisecond duration of the fast radio burst could then correspond to the brief lifetime of this unstable shock front before it dissipates into the surrounding medium. The beauty of these plasma instability models is that they can account for the intricate patterns we observe within the bursts themselves. The downward drifting subbursts, where each subsequent chirp starts at a lower frequency, could be a direct signature of an instability propagating outward through a region of declining plasma density. As the wave of synchronized particles moves away from the neutron star, it encounters ever thinner plasma, which changes the characteristic frequency at which the coherent emission can occur. The complex scintillation and scattering tails could be shaped by the turbulent, inhomogeneous plasma that is itself the product of these very instabilities. In this way, the detailed structure of the signal becomes a direct readout of the violent and complex plasma physics happening at the source, allowing us to use each burst as a cosmic laboratory to study processes that we could never hope to recreate on our planet. But what if the truth is even stranger than a Magnetar? What if the engine behind some of these bursts isn't a star at all, but a crack in the very fabric of the universe itself? This brings us to one of the most exotic and mind-stretching theories on the table, a clue that ventures from astrophysics into the realm of quantum cosmology. We're talking about cosmic strings' hypothetical, one-dimensional defects in space-time left over from the universe's fiery birth. Defects that could, in theory, snap with such violence that they broadcast their death throes across the cosmos as a fast radio burst. To grasp this idea, we need to rewind the clock to the very first fractions of a second after the Big Bang. During this period of intense heat and energy, physicists believe the universe underwent a series of phase transitions, much like steam cooling and condensing into water. But when a system undergoes a phase transition, it doesn't always settle into its new state perfectly. Defects can form. In the case of the early universe, one possible type of defect is a cosmic string, an unimaginably thin, incredibly dense filament of pure energy, a flaw in the geometry of spacetime itself. Think of it like a crack forming in ice as water freezes, but a crack that has mass and warps the space around it with its immense gravitational pull. These strings would be truly primordial entities, relics from a time before atoms or even particles existed, and they could theoretically span across astronomical distances. The physics of these objects is as bizarre as their origin. A cosmic string, if it exists, would have a thickness smaller than a proton but a mass of perhaps 1,000,000 billion tons per centimeter. This immense density means it would wield a gravitational field powerful enough to act as a gravitational lens, distorting the light from galaxies behind it. But more importantly for our mystery, these strings are under immense tension. They are thought to form loops that can oscillate violently or, in a truly catastrophic event, snap. When two segments of a string cross, they can reconnect and cut off a loop in a process called self-intersection. It is this sudden snapping or reconnection that could release a phenomenal amount of energy that is pumped directly into the creation of massive particles and intense electromagnetic radiation. This is where the connection to fast radio bursts emerges. The sudden release of energy from a snapping cosmic string could generate a powerful shock wave propagating through the surrounding intergalactic medium. This shock would accelerate electrons to relativistic speeds, and as these electrons are whipped around by magnetic fields, they would emit a brilliant, coherent burst of radio waves. The entire event would be incredibly brief, lasting only milliseconds, and the energy output would be more than sufficient to explain even the most powerful bursts we've observed from the distant universe. Because the string is a one-dimensional object, the emission would be naturally beamed, explaining why the signal is so intense from our specific line of sight. What makes this theory so compelling, despite its speculative nature, is its ability to explain some of the most puzzling outliers in the fast radio burst catalog. If a cosmic string snaps, it is a truly one-off event. The string is gone, and you would never see a repeat from that same location. This provides a natural explanation for the non-repeating class of bursts without needing to invoke a cataclysm that destroys a neutron star. Furthermore, because cosmic strings are a remnant of the early universe, they would be distributed throughout the cosmos, not just within galaxies. This could account for any bursts that might someday be localized to seemingly empty intergalactic space, a finding that would be deeply challenging for any stellar-based model. Of course, the cosmic string theory remains highly speculative. No one has ever directly detected a cosmic string, and their existence is predicated on specific, yet unproven, extensions to our current particle physics models. Finding definitive evidence for one would be a discovery of Nobel Prize-winning magnitude, fundamentally altering our understanding of particle physics and cosmology. For now, it stands as a captivating testament to the creativity of theorists and the profound depth of this cosmic mystery. It reminds us that to solve the puzzle of fast radio bursts, we must be willing to consider all possibilities, from the well-established physics of neutron stars to the wild frontiers of quantum gravity and the primordial universe. Yet this journey into the most exotic corners of theoretical physics inevitably invites a more provocative question, one that has captivated the human imagination since the very first burst was discovered. Could some of these signals be technological in origin? The idea that we might be detecting messages, or perhaps even the leakage from immense energy projects of an advanced civilization, is a hypothesis that, while far from the mainstream, is worth examining with both open-minded curiosity and rigorous scientific skepticism. The notion isn't entirely without precedent in our own history. When pulsars were first discovered in 1967, their unnaturally precise, repeating radio pulses briefly led the Cambridge team to nickname the source LGM-1 for Little Green Men. We now know pulsars are entirely natural, but that moment of wonder highlights a fundamental truth about exploration. The universe constantly presents us with phenomena that, at first blush, challenge our understanding of what is possible. The argument for an artificial origin often centers on several enigmatic properties of certain fast radio bursts. Their incredible brightness, combined with their millisecond brevity, suggests an emission process of startling efficiency, one that seems to concentrate a sun's worth of energy into a blink of an eye. Some bursts also exhibit band-limited emission, appearing to be confined to a specific, narrow range of radio frequencies, which to some ears sounds less like a natural cosmic event and more like a tuned transmission. The most famous repeater, FRB 121102, was even reported to have a curious, roughly 160-day periodicity in its activity, a cycle that could be interpreted as an operational schedule or a targeting mechanism. When viewed through a certain lens, it's not difficult to construct a narrative where these are not natural events but beacons, or perhaps the interstellar equivalent of a lighthouse beam sweeping past our vantage point in the galaxy. However, this is where the scientific method must rigorously separate captivating speculation from observable evidence. For every property that seems vaguely technological, there is a robust and well-supported astrophysical explanation that aligns perfectly with our understanding of plasma physics and compact objects. The band-limited emission is more readily explained by the signal filtering through a dense plasma screen near the source, a natural process that acts like a cosmic radio filter. The downward drifting subbursts are a classic signature of a shock wave propagating through a density gradient, not an engineered signal. The immense energy requirements, while staggering, are well within the theoretical limits for Magnetar starquakes and magnetic reconnection events, processes we are increasingly confident occur throughout the universe. Crucially, the definitive link between a fast radio burst and a known galactic magnetar in 2020 provided a natural anchor point, demonstrating that at least one prolific source of these signals is unequivocally a known type of neutron star. The most powerful evidence against an artificial origin, however, comes from the statistical distribution of the bursts across the sky and throughout cosmic time. Technological signals would presumably originate from sources within galaxies, the only places we expect life to emerge. Yet fast radio bursts are isotropic. They arrive from every direction in the sky with no preference for the galactic plane or the locations of nearby galaxies. They are spread evenly across the entire celestial sphere, a distribution that perfectly matches what we would expect from sources distributed uniformly throughout the entire volume of the observable universe. Furthermore, their dispersion measures show a clear correlation with distance. Bursts from farther away have higher dispersion measures, exactly as predicted by the amount of intergalactic material they should have traveled through. This creates a smooth, continuous relationship between redshift and dispersion that is incredibly difficult to reconcile with any coordinated technological activity. It would require not one, but thousands of independent civilizations, all at different stages of cosmological evolution, all deciding to build the same kind of impossibly powerful transmitter and aim it by chance directly at Earth. The sheer statistical improbability of this scenario makes a natural astrophysical origin overwhelmingly more likely. This is not to say the search for extraterrestrial intelligence is without merit. It is a profound and important scientific endeavor. But fast radio bursts, for all their mystery, do not currently present a strong candidate. They behave like natural phenomena. They are consistent with natural explanations, and they are now being used as natural tools to probe the cosmos. The true wonder lies not in the slim possibility that they are messages, but in the confirmed reality that they are natural cosmic fireworks of almost unimaginable power, emanating from the most extreme magnetic environments in the universe. They are a testament to the fact that nature, in its raw physical creativity, is capable of producing phenomena far more spectacular and awe-inspiring than anything we might invent. In solving their mystery, we are not closing a door on a cosmic conversation, but rather opening a magnificent new window into the fundamental forces that shape reality itself. Looking ahead to the next decade, the field of fast radio burst science stands on the brink of a true revolution, one that will be powered by a new class of observatories so advanced they will make our current telescopes seem like simple listening devices. The crown jewel of this coming era is the Square Kilometre Array, or SCAR, an international mega-project that represents the most ambitious radio astronomy endeavor in human history. Unlike a single dish, the SKA will be a vast network of thousands of antennae spread across two continents, South Africa and Australia, working in perfect harmony to create a collective collecting area of, as the name implies, approximately 1 square kilometer. This isn't just an upgrade, it's a quantum leap in our ability to listen to the cosmos, and it will transform our understanding of fast radio bursts from studying a few curious specimens to mapping an entire cosmic population in exquisite detail. The sheer scale of the SKA's sensitivity is difficult to overstate. It will be so incredibly powerful that it could detect an airport radar transmitter on a planet orbiting a star tens of light years away. For fast radio burst research, this means the telescope won't just be catching the loud, attention-grabbing events. It will be listening to the faint whispers of the cosmos, detecting bursts that are currently too weak or too distant for our present instruments to perceive. This will immediately solve the current selection bias, where we primarily study the most extreme and energetic examples simply because they're the only ones we can see. The SKA will reveal the full spectrum of these events, from the truly monstrous to the relatively quiet, allowing us to understand the complete life cycle and energy distribution of these sources for the very first time. But raw sensitivity is only half the story. The SKA's true superpower is its staggering field of view and its ability to process information. Where current telescopes like CHIME have already revolutionized the field by detecting thousands of bursts, the SKA is designed to discover millions. It will be able to scan the sky orders of magnitude faster than any existing facility, effectively acting as a perpetual motion machine for fast radio burst discovery. This immense survey speed means it won't just be waiting for bursts to happen. It will be constantly monitoring vast swaths of the sky, catching events almost as soon as they occur and providing a near real-time census of transient activity across the universe. This firehose of data will be so rich that machine learning and artificial intelligence will become essential partners in the discovery process, sifting through the torrent of information to identify and classify bursts automatically. This deluge of new detections will allow astronomers to perform population studies with a statistical power that is currently unimaginable. Instead of having a catalog of a few thousand events, we will have one containing millions. With that volume of data, subtle correlations and patterns that are currently hidden in the noise will become unmistakably clear. We will be able to create incredibly detailed maps showing how the properties of bursts, their energy, repetition rate, scattering, change depending on their host galaxy's type, age, and star formation rate. This will finally allow us to definitively answer the question of whether all fast radio bursts are born from the same basic engine, or if there are multiple, distinct formation channels operating in the universe. The population itself will become a precise cosmological tool, tracing the distribution of matter and the evolution of galaxies across cosmic time. Perhaps most excitingly, the SKA's exquisite angular resolution will provide what astronomers have been dreaming of since the very first burst was discovered: instantaneous, arcsecond level localization for virtually every event it detects. This means that for nearly every single fast radio burst, we will know its precise cosmic address within moments of its detection. We will be able to immediately identify its host galaxy, measure its exact distance, and then swing the world's most powerful optical, infrared, and X-ray telescopes to that exact spot to look for counterparts and afterglows. This will move us from the current era of painstaking, one-at-a-time localization into a new age of routine, precision astronomy for these events. The mystery of the one-off bursts will likely be solved within this data, as we will amass a huge sample of accurately located events, revealing without doubt the types of galaxies and galactic environments that produce these single, catastrophic explosions. The combination of precise localization and immense detection rates will also turn the SKA into the ultimate machine for testing fundamental physics. By collecting a vast number of bursts from the very edges of the observable universe, we will be able to use their dispersion measures to create a highly detailed three-dimensional map of the cosmic web, finally accounting for every last one of the universe's missing baryons. Furthermore, by comparing the arrival times of the highest and lowest frequency radio waves with incredible precision across billions of light years, the SKA will conduct the most sensitive test ever for the quantum nature of space-time, searching for any tiny energy-dependent variation in the speed of light that could reveal the granular structure of the universe at the Planck scale. In essence, the square-kilometer array will shift the entire paradigm of fast radio burst science. We will no longer be struggling to gather enough data to understand basic properties. Instead, we will be swimming in an ocean of information, using these events as refined tools to probe the universe itself. The mysteries that currently occupy us, what are they? Why do some repeat? Where do they come from? Will likely be solved in the SKA's first few years of operation, making way for even more profound questions about the extreme physics of neutron stars, the structure of the cosmic web, and the fundamental laws that govern all of reality. This next-generation telescope promises to not just solve the existing puzzle, but to open up entirely new chapters in our exploration of the cosmos, turning the enigmatic flashes we hear today into the foundational data points for the astronomy of tomorrow. And so we arrive at the grand synthesis, the final clue in our cosmic investigation, the search for a unified theory of fast radio bursts. After exploring 24 distinct pieces of evidence, from magnetars and plasma lensing to host galaxies and population statistics, we are left with a seemingly divided cosmos. On one side, we have the frequent, less energetic repeaters, likely powered by the persistent fury of young magnetars. On the other, the colossal, one-off blasts that suggest a final, cataclysmic demise. The central question now becomes one of profound simplicity and immense complexity. Are these two classes fundamentally different phenomena, or are we simply seeing different facets of the same incredible cosmic engine? The quest for unification is the ultimate goal of this scientific detective story, an effort to find a single theoretical framework that can explain this entire dazzling menagerie under one roof. One of the most compelling pathways toward unification involves a simple shift in perspective literally. What if the defining difference between a repeater and a one-off burst isn't the source itself, but our particular viewing angle? Imagine a magnetar as a cosmic lighthouse, with its immensely powerful beams of radiation shooting out from its magnetic poles. If those beams are narrow and we happen to be positioned directly in their path, we would see a brilliant, incredibly intense flash each time the beam sweeps across our line of sight. But if the magnetar's spin axis is misaligned, we might only catch glancing blows, weaker bursts from the edges of the beam, or nothing at all. In this model, a repeater could simply be a magnetar whose beams we are consistently immersed in, while a one-off event might be a source whose main beam only flashed across our vantage point once, never to return. The source is identical, our perspective is what creates the classification. This geometric interpretation gains further depth when we consider the source's environment. A young, hyperactive magnetar is often enshrouded in a dense nebula of its own making, a chaotic cloud of plasma and magnetic fields. This nebula doesn't just surround the star, it can confound and distort its emissions. A burst aimed directly at us might punch through this shroud relatively cleanly, appearing as a simpler, brighter flash. However, a burst that is initially off-axis might ricochet within this turbulent cavity, scattering off pockets of plasma and taking multiple paths before finally escaping. This could explain the incredibly complex, multi-peaked structure seen in some repeaters. The signal isn't a single clean shot, but a complex echo chamber effect. The one-off bursts in this view might be the clean, direct hits that manage to avoid this scattering, making them appear simpler but more powerful. The same engine, the same fuel, but a different journey through the maze around it creates the diversity we observe. Another powerful unifying idea centers on evolution. Perhaps what we are witnessing is not different types of sources, but different chapters in the same cosmic life story. A magnetar is not a static object. It is born in violence and evolves over thousands of years. In its youth, it is unruly and energetic, spinning rapidly and possessing a magnetic field at its maximum strength. This is its repeater phase, a period of frequent and dramatic outbursts as its crust adjusts to immense stresses and its magnetosphere settles down. During this tumultuous adolescence, it fires off bursts regularly, but as the magnetar ages, its spin slows and its magnetic field gradually decays. The starquakes become less frequent, the energy available for bursts diminishes. The once hyperactive youngster settles into a long, quiet middle age. In this framework, a one-off burst could be the magnetar's final, grand performance, a last, catastrophic crustal collapse, or a magnetic avalanche that releases a significant fraction of its remaining energy in one glorious terminal explosion. After that, it falls silent forever. We are therefore seeing the entire lifespan of these magnetic monsters, the frequent outbursts of youth and the rare, violent death throes of old age, all from the same type of object. This evolutionary picture is beautifully supported by the diversity of host galaxies. The repeaters are often found in young, star-forming dwarf galaxies, the perfect stellar nurseries for birthing new, active magnetars. The one-off events, by contrast, are also found in ancient, quiescent galaxies where star formation ceased billions of years ago. This is exactly what an evolutionary theory would predict. The old galaxies host the old, evolved magnetars that have only one final burst left in them, while the young galaxies host the newborn, energetic ones that are constantly throwing tantrums. The universe is showing us a complete demographic survey, from the bustling maternity wards to the quiet retirement homes for stellar remnants. The ultimate unified model will likely be a hybrid, a sophisticated tapestry woven from these threads of geometry, environment, and evolution. It suggests that a magnetar's personality, whether it appears to us as a repeater or a one-off, is not determined by a single factor, but by a combination of its age, the density and magnetization of its surrounding environment, and the pure chance of our celestial vantage point. This comprehensive framework doesn't just solve the mystery, it elevates fast radio bursts from isolated curiosities to powerful diagnostic tools. By carefully analyzing a burst's properties, its energy, its repetition rate, the complexity of its structure, we can now begin to infer the age of the source, the density of its environment, and even its orientation in space. The burst becomes a cosmic passport, detailing the life and times of the object that created it. The search for a unified theory is more than an academic exercise. It is the culmination of our journey to understand not just what these signals are, but what they can teach us about the life cycles of the universe's most extreme and mysterious inhabitants. And so our journey through these 25 cosmic clues brings us full circle, from that first astonishing blip in archived data to the sophisticated unified theories taking shape today. We began with the raw discovery, the Lorimer burst, a single event that revealed these millisecond flashes packing more power than our sun emits in 80 years. We saw how their incredible brevity makes them both a detective's nightmare and a dream, their fleeting nature guarding secrets while their dispersion acts as a cosmic measuring tape, placing them billions of light years away in the distant universe. The revelation of repeating bursts shattered the cataclysm model, proving some sources could fire again and again, while revolutionary telescope arrays like CHIME and ASKAP transformed mystery into statistics, delivering thousands of events and allowing us to see the population as a whole. We delved into the environments, tracing bursts back to their host galaxies and finding a stunning diversity, from turbulent dwarf galaxies to serene elliptical giants, each whispering different stories about their origins. The smoking gun arrived from within our own Milky Way, as a known magnetar unleashed a simultaneous radio and X-ray burst, definitively linking at least one class of these events to these extreme stellar remnants. We explored the intricate physics within their signals, the complex time-frequency structures, the downward drifting subbursts, the polarization that acts as a cosmic compass, each pattern a detailed readout from the heart of a cosmic earthquake. The search for periodicity revealed potential cosmic clocks, hinting at orbital dances, while the immense energetics forced us to consider engines of unimaginable power, focused into tight beams by natural cosmic lasers. The journey through scattering and scintillation showed how the turbulent interstellar medium smears these signals, while plasma lensing revealed how that same material can sometimes act as a colossal magnifying glass, amplifying bursts to apparent impossibility. The multi-wavelength hunt, often finding silence, ruled out certain cataclysms and pointed toward more efficient, coherent emission processes. The statistical power of vast catalogs allowed us to see the clear dichotomy between repeaters and one-offs, suggesting a diverse zoo of sources, while the application of these signals as tools revealed the universe's missing baryons hiding in the warm, hot intergalactic medium. We even ventured to the edge of physics, where these bursts test Einstein's relativity and probe the possible quantum grain of spacetime itself. We considered the violent dances of binary systems and the telltale link to supernova remnants, the chaotic nurseries where magnetars are born. The role of plasma instabilities provided a microscopic mechanism for generating coherent emission, while the most exotic theories, like snapping cosmic strings, reminded us to keep our minds open to the wonderfully strange. The question of artificial origins was examined and set aside, not as a dismissal of possibility, but as a celebration of nature's own spectacular creativity. And we look to the future, to the era of the square-kilometer array, which promises to transform these enigmas from objects of mystery into refined tools for mapping the cosmos. Each of these 25 clues is a vital piece of the puzzle, a testament to the relentless curiosity and collaborative genius of scientists worldwide. In just over a decade and a half, we have moved from a state of complete bewilderment to a framework of solid understanding, a pace of discovery that is breathtaking. The story of fast radio bursts is far from over. Every answered question opens new, deeper mysteries. It is a powerful reminder that the universe is still wild, still unknown, and still capable of astonishing us. So stay curious, look up at the night sky, and remember that every time we unravel one cosmic secret, we are not reaching an end. We are simply preparing for the next great question, ready to be asked by the next generation of explorers.